Imagine just for a moment that right in front of you sits the largest camera ever built in the world, capable of capturing an astonishing 3200 megapixel digital image in a single shot. If you had something like that at your fingertips, what would be the very first thing you would want to photograph? Would you point it toward distant stars far beyond our reach, mysterious glowing nebulae drifting through space, or perhaps the detailed surface of the moon? And yet, SLAC engineers chose something completely unexpected for their test shots. Unbelievably, a cauliflower. Hello everyone! Yes, that's right. A type of cauliflower known as the Romanesco was captured in stunning detail, displayed beautifully across an incredible array of 378 separate screens. In fact, it took that many displays just to show the image at its full true-to-life resolution without losing any detail. Alongside the cauliflower, scientists photographed the famous Flammarion engraving, plus an image of astronomer Vera Rubin working. They even went a step further and created collages using photos of themselves, pictures of people they admire, and the official logos of the organizations involved in the project. Welcome to our channel! Thank you so much for watching. So, why did the engineers choose such unusual subjects for their images? How exactly does this extraordinary camera work, and where is it actually going to be used in the real world? We're about to walk you through all of it in detail. So let's dive right in and get started. Camera capabilities. The team at SLAC has achieved something remarkable, capturing the largest non-composite photograph ever taken and setting a new world record in the process. The resulting image is so incredibly detailed that it could clearly distinguish a golf ball from as far away as about 15.5 miles. What makes this even more impressive is that the image wasn't taken with a fully assembled camera. Instead, it was captured using only the optical sensor itself. This sensor measures roughly 25 inches across and is built from a total of 189 individual imaging sensors working together. To understand how the camera's focal plane, in other words, the surface where the image is actually formed, would function, the team used this sensor alone to generate images. The sensor works by capturing light that is either emitted or reflected by objects, and then converting that incoming light into electrical signals. Those signals are later processed and used to construct a full digital image with incredible precision. Interestingly enough, a similar type of sensor is already built into the smartphone you carry around every day. That said, the sensor developed by SLAC is, of course, vastly more complex and far more advanced in every way. Each individual imaging sensor that makes up the optical array has a resolution of 16 megapixels on its own. That level of resolution is roughly comparable to the image sensors found in many modern digital cameras today. These imaging sensors are grouped into square modules, with each module consisting of 9 sensors, along with the supporting electronics required to operate them. The gaps between these modules are incredibly small, measuring less than the width of 5 human hairs placed side by side. The complete sensor is made up of 25 of these modules assembled together with extreme precision. Of those, 21 directly capture images, while the 4 corner modules are dedicated to guiding and fine-tuning focus. Experts note the entire system was engineered with extreme precision, achieving a highly optimized design. The focal plane itself is enormous, large enough to capture a patch of sky that could comfortably fit 40 full moons, and at the same time, it remains remarkably flat across its entire surface. Thanks to this design, the finished camera is capable of producing images that are both extraordinarily sharp and packed with fine detail. The imaging sensors are so sensitive that they can detect objects up to 100 million times dimmer than what the human eye can perceive. With that level of sensitivity, it would theoretically be possible to detect light from a single candle from thousands of miles away. The first images. But why, of all things, was a cauliflower chosen to be the very first subject photographed? The scientists decided to capture Romanesco specifically because of its incredibly unusual and fascinating structure. The florets of Romanesco resemble a striking fractal pattern that immediately catches the eye. Each individual bud is actually made up of smaller buds repeating the same shape, and together they form a beautiful logarithmic spiral across the entire surface. It really is something that feels like a mathematician's dream brought to life. Because of this intricate structure, the cauliflower allowed the team to carefully evaluate just how well the camera's sensor could capture extremely fine details. Since the camera had not yet been fully assembled and still lacked both a lens and shutter, the team improvised by using an opaque box with a tiny opening about 150 microns wide, slightly thicker than a human hair. They placed the cauliflower inside the box and projected its image through that small opening directly onto the focal plane. Before doing that, the sensor itself was placed inside a cryostat, a device designed to maintain extremely low temperatures and cooled down to about -148 degrees Fahrenheit, which dramatically reduced image noise. Using this exact same method, the team went on to capture several other images as well. One of them is a beautiful engraving showing a pilgrim peering beyond the edge of the world, a scene that appears at first glance to come from the Middle Ages, though that is not actually the case. This engraving was first published in the 19th century in a book by Camille Flammarion, who was well known for bringing science to a broader audience. Although the work is officially attributed to an unknown artist, many historians suspect that Flammarion himself may have created it. In fact, the engraving style and carving tools belong to a later period, specifically the late 18th century. So while it's not a truly medieval image, it still reflects the kind of outdated worldview that was once widely believed in earlier times. And now, being able to view that very image in a stunning 3200 megapixel resolution feels deeply symbolic in its own way. Humanity, take a good look. Just how far we've come is nothing short of extraordinary. As for the other images, it's easy to understand why the scientists created collages using photos of themselves along with the logos of the organizations involved in the project. But why then did they choose to include a photograph of Vera Rubin? She was an American astronomer who dedicated her work to studying the rotation of galaxies. Her research ultimately laid the foundation for uncovering the mystery of dark matter. So what exactly is her connection to all of this? As it turns out, this high-performance sensor belongs to a camera built for a newly operational telescope in Chile. Originally part of the LSST project, the observatory itself was renamed to honor Vera Rubin. So including her image in these tests serves as a tribute to an exceptional scientist and her lasting contributions. Challenges of the telescope. A project of this enormous scale naturally requires an extraordinary amount of time and effort to bring to completion. For example, the camera designed for this telescope has been under development since as far back as 2015. The camera was finally completed in 2024, and in May, after a long and careful journey, it was safely transported to an observatory located high in the mountains of Chile. Following meticulous calibration, the telescope's breathtaking first-look images of the universe were finally revealed in June 2025. The released imagery was nothing short of breathtaking in its beauty. Across a massive field of view, countless stars and galaxies were captured with stunning clarity, sparkling like jewels. Amazingly, a single image contained millions upon millions of stars and galaxies all at once. Regions of space that previously required several days of observation by earlier space telescopes can now be captured by this camera in a much shorter time and with a far wider field of view. After many years of development, along with delays caused by the pandemic, the dedication and hard work of countless people have finally paid off. On top of that, scientists are eagerly anticipating the discovery of so-called rogue planets, worlds that drift through space without orbiting any star. Some theories even suggest that their numbers could exceed the total number of stars in the Milky Way galaxy. These lonely ghost planets wandering silently through the darkness might actually exist in vast numbers surprisingly close to Earth, and at last, that mystery may finally be within our reach to solve. And now, in 2026, the long-awaited 10-year legacy survey of space and time is finally getting underway. There's a lot to look forward to. With a telescope equipped with such an incredibly powerful camera, what exactly will we be able to achieve? At the observatory, this telescope, paired with its massive 27.6-foot mirror, will carry out a large-scale sky survey known as the Legacy Survey of Space and Time. Interestingly, the camera itself retains the original LSST acronym. The survey will continue over the course of 10 years, with the camera capturing panoramic images of the southern sky once every 3 nights to build an ever-growing dataset. In total, the images are expected to record as many as 20 billion different galaxies. Over the course of the survey, the telescope will generate around 200,000 images every single year. By repeating this process again and again, scientists will effectively create a massive time-lapse movie of the universe itself. This will allow them to track moving asteroids and observe exploding stars as they change in real time. In other words, an incredible wave of breathtaking new images of the universe is about to unfold before our eyes. At the same time, it will be essential to develop the most efficient ways possible to process this overwhelming volume of data. Of course, this kind of advanced equipment is not designed solely for capturing beautiful images. The survey will deepen our understanding of how galaxies form and evolve, while also helping to test different models of dark matter and dark energy and uncover their true nature. The observatory will also serve several other important purposes. For example, it will play a key role in planetary defense by detecting potentially hazardous asteroids early, helping to protect our planet from possible impacts. However, in order for the Vera Rubin Observatory to operate at its full potential, there is a major obstacle that cannot be ignored: the growing number of artificial satellites. In recent years, the number of satellites in low Earth orbit has increased dramatically. Because these satellites reflect sunlight, they can interfere with observational data, especially for telescopes like this one that operate in visible and infrared wavelengths. Let us hope that astronomers will find a way to overcome this challenge. And let's all root for the expert teams working on this issue so that the telescope can truly demonstrate its full capabilities. If you enjoyed today's video, please take a moment to leave a like and share it with your friends. Thank you all so much for watching. And until next time, we'll see you again soon. Goodbye.